Good morning, dear ladies and gentlemen. Let me thank EGVIA, AirTruck, and the European Commission for organizing this conference. Our project acronym CVOLVA stands for Connected Electric Vehicle Optimized for Life, Value, Efficiency, and Range. And our project responds to the first topic of the 2018 Green Vehicle Call, Integrated, Brand-Independent Architectures, Components, and Systems for next-generation electrified vehicles optimized for the infrastructure. Our presentation will quickly be structured into three major parts: an introduction of the project, an overview of what has been achieved so far, and then what is yet to come as next steps. Our CVOLVA objectives are to make a leap forward in users' trust with providing smart new functionalities that enhance the efficiency and the reliability and comfort of using electric vehicles. To make future electric vehicles more affordable, as they will fit the user's needs without being over-engineered. To validate advanced components and systems along with their novel control strategies and functionalities in a high-speed wireless connected scenario. And for sure, an impact assessment of the progress made with the demonstrated innovations of the CVOLVA project to improve cost, efficiency, and longevity of the electric vehicles. To meet these objectives, CVOLVA takes a user-centric approach for optimizing the development and operation of electric vehicles. The idea is to have a widely integrated thermal management, reusing the heat released by battery, electronics, and powertrain components for heating. Then, through connectivity features, the vehicle should receive up-to-date weather and traffic information for more efficient energy management, run the optimal route, make reservations for a charging point, and communicate state of X, charge and health, for example, information with the OEM cloud. Such data will help then the OEMs and its contractors understand even better the very usage of the vehicles, understand what users really need, so they can develop a better suited next generation of that vehicle. We have a typical project architecture with three vertical work packages related to the demonstration vehicles of Fiat and Ford, bringing the base vehicles to be modified with the features developed in this project, and Bosch using a brand-independent prototype rolling chassis as a component carrier. Then come the horizontal overarching work packages, with work package 1 setting the scene for a connected energy and thermal management system, use cases, interfaces, etc. Work package 2 setting up frameworks, methodologies, models, and tools for the optimization of the electric and thermal management and assessment of connected electric vehicles. Work package 6 for validating and verifying the demonstrators and to assess the energy savings obtained with the new features. Work package 7 and 8 deal with communication, dissemination, exploitation, and with project management, respectively. Because work package 6 will have its major activity in the last year of the project, we will focus today on the outcome of work package 5 of work package 1 and up to 5 that, according to the schedule, could already provide results, and a little on work package 7. Work package 1 has specified the requirements for brand-independent connected energy and thermal management. In close collaboration of all partners, we selected, defined, and specified brand-independent electric and electronic interfaces, as well as standards for the communication with the cloud and external servers. Also, we developed use cases for the commercial vehicle in work package 4 and for the A-class passenger car in work package 5. We developed brand-independent, user-centric requirements and system-level requirements for the system architecture. And we defined KPIs for later evaluation. All deliverables were successfully completed within the first reporting period and have been published. Work Package 2 builds on Work Package 1, but had to go hand in hand with it for schedule reasons. Based on previous research results, it created a base vehicle simulation platform for connected vehicles with eco features, eco routing and eco driving, and with access to web services. It allows selecting and sizing components and the optimization of the energy and thermal management strategy, for example, for cabin, battery, and the powertrain of the electric vehicle. The model architecture and its submodels are brand independent, so the model is matched to the different vehicles through parameterization. Using real-world driving profiles from the cloud-connected servers, we can assess the technology packages, including eco-driving and eco-routing, in terms of energy efficiency and effectiveness of measures to keep temperatures in the desired boundaries. In Work Package 3, Bosch performs system and component testing using an electric vehicle prototype component carrier. That component carrier is made available by a collaborate project between Bosch and Benteler and used for the purposes of Seevolver. It shall be used to test functions of other work packages in the Seevolver project to assist in right sizing of components. With the first prototype, initial component testing could be performed in September 2020. The next steps will consist of commissioning of an improved prototype with predictive thermal systems, which is already ongoing, that shall represent the functionalities of the Seevolver project. And functions of the Bosch vehicle control unit are in progress to implement functions of Seevolver partners. Work Package 4 is led by Ford and deals with the system development, vehicle upgrade design, and build and demonstration of a light-duty commercial vehicle. The first use case is using the battery electric transporter for a parcel delivery service in urban and peri-urban environment. The battery capacity fits to this purpose, and the frequent stop-start operation is the ideal application for a BEV. The challenge, however, is using this vehicle for the occasional 700-kilometer day trips, like the use case of a craftsman one-day job 350 kilometers away. In the morning, this craftsman drives 350 kilometers to the construction site. The vehicle can be with a charging stop underway. The vehicle can be charged at lower power during the work on the construction site. And in the evening, the craftsman drives home again with a charging stop, completing his 700 kilometers round day trip. The base vehicle is instrumented and ready for baseline testing, and the targeted thermal system is defined and the corresponding components are selected. The novel control strategies are currently assessed for the Work Package 4 use cases. In Work Package 5, CRF tackles the scientific and research content foreseen in the proposal with the combination of the two demonstrator vehicles shown here. We are upgrading the demonstrator vehicle you may remember from the Optimus project with advanced thermal management strategies based on eco-routing and evaluate the impact of eco-driving. And battery preconditioning and fast charging will be evaluated using the new Fiat 500 battery electric vehicle. On the Seevolver Optimus vehicle, the extended vehicle architecture and the cloud connection are ready. The demo vehicle upgrade has started with maintaining the heat pump and installing the camera for advanced cruise control. And for the new 500 battery electric vehicle, the effect of the heat storage has been evaluated by simulation and is proven by measurements, and now the vehicle upgrade is under design. So among the next steps are certainly the completion of Work Package 2 with the multi-level thermal and energy management strategy. We have to complete the vehicles and then start the calibration and testing activities. And among the future research needs, let me highlight The tools and methods to handle and ensure the durability for vehicles with fast charging systems are priority also by simulations and by component testing. And also setting up digital twins in the cloud, so the battery in the cloud with AI that are AI based and machine and support everything with machine learning. So, and if you ask me how far we are from market introduction, it depends on what we are looking at. So certain components can probably be available 2 to 3 years after the end of the project, but also the cloud functions could last until 5 years after after the end of project, depending on the standards and harmonization. As a consortium, we intend to follow on with demonstration projects in different environments and with research and innovation on power electronics, but also on this before mentioned twin in the cloud. And we believe that thanks to the EU financial support, we have saved between 2 and 5 years of development time. Let me point out to the dissemination efforts that we are performing in a concerted manner in the Evolve cluster, which is organized by our sister project Achilles with Stella Arapoglu. Please look up the website, just scan the QR code. And certainly also thanks again to IGVI and the European Commission for funding. And likewise, this code here will take you to the Evolver homepage. With ending this presentation, I would like to thank all partners in the project for the excellent collaboration in these first 2 years of the project. I look forward to the 18 months yet to follow. Thank you all for your attention, and thank you, Luca Fiola at INEA, for your kind support and collaboration.